Real Analysis Lecture 14 on Squeeze Theorem by Dr.P.Ramulu, Head Department of Mathematics, MBS Government Arts Science College, Mahunagar. Okay. Already we have discussed about the sequence, limit of sequence, and problems of sequence. Now I am going to discuss about the Squeeze theorem. Okay. What is Squeeze theorem? For finding the convergence of sequence, now I am going to use Squeeze theorem, right? I want to use Squeeze theorem to solve convergence of some different type of sequence, right? So, linear analysis lecture 14 on Squeeze theorem by Dr. P.Ramulu, Head Department of Mathematics, MBS Government Arts and Science College, Mahabubnagar. What is Squeeze theorem? What is Squeeze theorem? I am taking that here Sn Sn Tn Un or three sequences. I am taking that Sn comma Tn comma Un are three sequences. First one so I want to take that Sn is less than or equal to Un less than or equal to Tn. Sn less than or equal to Un less than or equal to Tn for n greater than or equal to some m or n greater than or equal to some k, whatever we will get that. Second one lim Sn equal to L. Lim Sn equal to lim Tn equal to L. Then lim Un equal to Sn comma Tn comma Un are three sequences. First one Sn less than equal to Un less than equal to Tn for all n greater than equal to k. Second one lim Sn equal to lim Tn equal to L, then lim Un equal to L. So this thing I would like to say, right? Sn comma Tn comma Un are three sequences. Sn less than equal to Un less than equal to Tn for all n greater than equal to k, which implies first one lim Sn equal to lim Tn equal to L, then lim Un equal to L. So this is the statement theorem. The Squeeze theorem is also called Sandwich theorem. The Squeeze theorem is also called Sandwich theorem. That way, for finding the convergence of sequence of Un, I want to find the convergence of other sequences Un and Tn. If I apply lim of Sn and lim of Tn that equal to L, then lim of Un equal to L. So for finding these two sequences, if both converge to the same limit, I will say that the convergence of Un is the same. So this is way it is very important Squeeze theorem, right? This theorem is called Squeeze theorem. Squeeze theorem, or you can that Squeeze theorem, or also called Sandwich theorem. So Sandwich theorem. squeeze theorem or Standard's theorem. This theorem is called squeeze theorem or Standard's theorem, right? Now idea proof is I want to take that Sn comma Tn use three sequences. Sn less than equal to Un less than equal to Tn for all n greater than equal to k. Second one limit of Sn equal to limit of Tn equal to, then I want to show that limit equal to, right? I use differential limit. What is limit of sequence? So already you know that. I have explained again. For every epsilon greater there exists epsilon L plus that mod Sn minus Sn L less than epsilon for all n greater equal to m. Similarly here Tn also you can take that. By using these two conditions I want to show that limit of n equal to this, right? So statement an here I'm taking differently. Okay, here I'm taking differently. Same properties, nothing will happen, but here I'm taking that an comma bn sn are three sequences. An comma bn sn are three sequences such that an less than or equal to sn less than or equal to bn for all n greater than n. Second one lim of an equal to l, lim of bn, then lim sn equal to n. Okay, an comma bn comma sn three sequences such that an less than or sn less than or equal to bn for all n of n, lim a equal to l and lim bn equal to, then lim sn equal to l. Same condition, instead of an bn I am taking here, there I took that an sn, right? So let an comma bn sn three sequences, an less than or equal to sn less than or equal to bn for all n belongs to n. Let lim n equal to l. Lim n equal to nothing but what is definition? For every epsilon greater than 0, there exists m1 belongs to z place such that mod an minus l is less than epsilon for all n greater than or equal to m1, which implies mod an minus l is less than epsilon for all n greater than or equal to m1, which nothing but l minus epsilon is less than an less than l plus epsilon for all n greater than or equal to m1, that is equal to 1. So this I am writing 1. Second one, lim bn equal to l, which implies for every epsilon there exists m2 belongs to z plus such that mod bn minus l is less than epsilon for all n equal to m2, which is nothing but mod bn minus l is less than epsilon for all n equal to m. Here l minus epsilon for bn is less than l plus epsilon for all n equal to m, right? If my condition, if you take here for n equal to k, I will write here m is equal to maximum of m1 m2, or there you can write k also, nothing will happen. So which implies what happen? L minus epsilon, if it is there k, sometimes we will take here for n equal to k, we can write here maximum of m1 m2 and k. So which implies what happen? L minus epsilon is less than an, is less than sn, is less than bn, less than epsilon. So from 1 you can observe here L minus epsilon is less than a. From given condition, what we know that an less than or equal to sn for all b less than or equal to bn. So L minus epsilon is less than sn less than bn. Already from 2, what we know that bn is less than l plus epsilon. By using 1, 2, 3, I am writing the L minus epsilon is less than an. From given condition sn less than or equal to bn. From definition of limit, what we know that L plus epsilon for all n greater equal to m. From star 1, 2, 3. Which nothing but L minus epsilon is less than sn is less than l plus epsilon for all n greater equal to m. Which nothing but mod sn minus l is less than epsilon for all n greater equal to m. For every epsilon greater 0, there exists m belongs to z place such that mod sn minus l is less than epsilon for all n greater equal to m, which implies lim sn equal to l, hence proved theorem. Okay, so this is the full, right. Here show that lim of 1 by n sin n equal to 0. Show that lim of 1 by n sin n equal to 0. For this, I am taking that what could I show? I want to show that question is, my question is we have to show that lim of 1 by n sin n equal to 0, right? So this thing over, I will see lim of sin 1 by n, lim of 1 by n sin n equal to 0, I want to show that. Okay. For this, what I am transferring, I know that mod sin x is less than or equal to 1. By use that condition, so answer is I know that mod sin n is less than or equal to 1, which implies, what we know that, which implies minus 1 is less than or equal to sin n less than or equal to, if I multiply by 1 by n, 1 by n, what I am doing here, so minus 1 by n, one by n sin n is less than or equal to 1 by n. If I apply limit, I know that this is Sn less than or equal to n less than or equal to Vn. Here it is for oral elimination. If it is here, I'm taking that this nothing but already we know that the first condition over an less than or equal to Sn. This is an less than or equal to Sn less than or equal to Vn. Sn nothing but this. And second condition I am doing that and lim of minus 1 by n equal to 0. We know that. Lim of apply 1 by infinity equal to 0. That equal to, already we know that limit of 1 by n. Lim of 1 by n. Both are 0. Which implies by squeeze theorem, right? By squeeze theorem, by squeeze theorem, what means that what we know that by squeeze theorem, these both are same. This limit same, the middle one also will be converges to 0. That means if I apply limit here, what happen? Lim of one by n lim of 1 by n sin n equal to 0, right? So this is where so important of Q theorem, right? While we finding this, I want to find other two limits. If it is both converges to the same limit, this also converges to same limit. Therefore, we show that lim of 1 by n sin n equal to 0. This is the very importance of the Q theorem. This kind of different problems, so now we are going to solve by using Q theorem. So same sin n less than 1, minus 1 less than sin n minus 1 1 by sin n 1, this is 0, this is 0, the middle one also 0. By squeeze theorem, we know that lim of. Show that lim of right lim of sin n pi by 3 by root n equal to 0. Root n equal to 0. Right. This thing I would like to show. Same here, I am taking sin n pi by 3 is less than or equal to 1. If I take sin x is less than or equal to 1, in place of x we have n pi by 3, that is less than or equal to 1. Minus 1 less than or equal to sin n pi by 3 less than 1. So I am dividing by this equality by root n, then minus 1 root n less than or equal to sin n pi by 3 by root n less than or equal to 1 by root n. This will be 0, this will be 0. By squeeze theorem, the middle one also 0. By squeeze theorem, middle one also 0. Right. Show that lim of cos n pi by n equal to 0. Show that the lim of cos n pi by n equal to 0. Right. I would like to show this is equal to 0. Right. So for this, what can I show? Let I am considering sin n pi by n is less than or equal to 1. mod of sin n pi equal to, already we know that cos x and sin x is less than equal to 1. This mod of cos n pi by n is less than equal to 1. Cos n pi by n, right? N pi, okay. Here I made 1 minus 1 less than cos n pi by n. Here what is the power n pi by n? Less than, sorry, cos n pi only, not here, need not write here, here only cos n pi. So minus 1 less than cos n pi by less than 1. Minus 1 less than cos n pi by n less than, I am dividing this inequality. This is no n here. Here also only cos n pi. Mod cos n pi less than equal to 1. Minus 1 less than cos n pi. So that equal to this limit 0 and this is 0. The middle one also 0. By skew theorem, cos n pi by n is 0. Okay. Show that lim of 1 by n plus 1 whole square plus 1 by n plus 2 whole square plus so n plus n whole square is equal to 0. For finding these kind of problems, so it is very important, right? So why? Because if it is find limit of middle one, the other thing will be easy, right? Here I am considering 1 less than or equal to m less than or equal to n. Here I am considering 1 less than or equal to m less than or equal to 1. So by using the inequality, I want to show this by applying Cauchy theorem or Standard's theorem. What I am adding here, I am adding both sides n, 1 plus n, which is less than or equal to n plus m, right? Squaring this inequality, 1 plus n whole square, n plus m whole square, n plus n whole square, by 1 plus n whole square, which is greater than or equal to 1 by n plus m whole square, which is greater than or equal to 1 plus 2n whole square, right? So by inequality this, right here, which implies here, what will this inequality I am writing here, 1 by 2n square nothing but 4n square, which is less than or equal to 1 by n plus m whole square, which is less than or equal to 1 by n plus 1 whole square. If m is equal to 1, then what happen, 1 by 4n square, which is less than or equal to 1 by n plus 1 whole square, which is less than or equal to 1 by n plus 1 whole square. If m is equal to 2, what happen here, 1 by 4n square, less than or equal to 1 by n plus 2 whole square, which is less than or equal to 1 by n plus 1 whole square, right? If m is equal to n, what happen here, 1 by 4n square, less than or equal to 1 by n plus n whole square, less than or equal to 1 by n plus 1 whole square. By adding above any inequalities, then what happen here, 1 by 4n square, 4n square, 4n square, these are n times. Next one, 1 by n plus 1, 1 by n plus 1, 1 by n plus 1 whole square, plus these are n times, n by n plus 1 whole square, right? Now, n by 4n square nothing but 1 by 4n, this is nothing but 1 by n into 1 plus n square. The middle one is same given sequence. 1 by 4n is equal to 0, and this is also 0, this is also going to 0 by Sandwich theorem or Skews theorem, right? Similarly, you have to show this also, lemma of 1 by n plus 1 whole square plus 1 by n plus 2 whole square plus as a plus 1 by n plus n whole square, okay? So as it is same, this also 0, I will show that. Now I am going to show that 1 by root n square plus 1, 1 by n square plus 2, 1 by n square plus n, right? So this thing I want to show, right? Same problem, I want to show this is equal to 1, okay? 1 by n square plus 1, 1 by root n square plus 1 plus 1 by root n square plus 2, that is 1 by n square plus n, right? So I am taking 1 less than or equal to m less than or equal to n. So I am adding n square both sides, n square, n square, n square, okay? See, I will show how it is. One problem, if it is clearly, I want to show that a question again. We can, if we observe quickly, it is easily lemma of n square plus 1 plus n square plus 2 1 by n square plus n equal to 1. Show that this is equal to 1. We have to show this is equal to 1. For this, I am considering right solution. So for this, I am considering here 1 less than or equal to. For these kind of problems, we must take like this only. 1 less than or equal to m less than. Here we have n square. That's why I am adding both side n square, right? N square plus 1, which is less than or equal to n square plus m less than or equal to n square plus m. Okay, so I'm adding both sides n square plus 1, n square plus m, n square plus n, right? So which implies squaring both sides, square root both sides. This inequality what I am doing here, n square plus 1, which is less than or equal to n square plus m right, which is less than or equal to n square plus m. Right. Here what I am doing here, n square plus 1 less than or equal to. I am reciprocating this. Okay, so that means 1 by n square plus 1. If you reciprocating, the sign will be changes. 1 by n square plus m, which is greater than or equal to 1 by so what happened here, n square plus n, right, which implies again what will happen is simply I am rewriting this inequality. Okay, I am writing the same inequality, nothing will happen. I want less than n square plus n, which is less than or equal to 1 by n square plus m, which is less than or equal to 1 by n square plus 1. So this sign will be changes. Either this come this side, this come this side, the sign also changes same. Both will be the same. Right? So I am putting m is equal to 1. If m is equal to 1, then what happens, 1 by n square plus n, 1 by n square plus 1 is less than or equal to 1 by n square plus 1. If I write n equal to, right, m is equal to 2, same inequality will get here. The middle term is, so this will be same, which is less than or equal to here 1 by n square plus 2, which is less than or equal to 1 by same this thing, right? So 1 by square root of n square plus n, here square root of n square plus 1. Right? This will be same. Dash. So up to, if I write if m is equal to, if m is equal to n, so then what happen here? So m is equal to n, then what happen? 1 by square root of n square plus n less than or equal to 1 by, so n square plus, sorry, n square plus m, which is less than or equal to 1 by n square plus 1. Okay. By adding above inequalities, simply adding here above inequalities, so this will be get, where is this 1 1 1, here how many times are there? So adding above inequalities, okay, I am adding above inequalities. What we get? 1 2 up to n, right? How many inequalities are there? N inequalities. If I add left side, what we get here? N times of n square plus n, which is less than or equal to, if I add middle terms, so then what happen? 1 by n square plus 1, n square plus 2, that has n square plus 1. Here the middle will come, so n square plus 1 plus 1 by n square plus 2 plus 1 by n square plus n, less than or equal to, here right hand terms also, how many terms here we have? N terms, right? So that means if I add all terms, so what will get? N by n square plus 1. Right? Now apply limit for this, right? Apply limit, this term, this is Sn, an, this is Bn, this is this term is, you can take that, this is Sn, this is Bn, this is An, right? Apply limit to this. Apply limit to this. Limit of this thing, n by n square plus n. That equal to, here square root means square root means If I take common out from this, limit of 1 by, if I take n square common out here, if n square common out, the square root of n square will m come, n will cancel out. Here we will get 1 plus n by n square equal to n. The value of this equal to 1 by square root of 1 plus 0. Already we know that lim of Sn equal to lim root of Sn. Lim Sn, then lim root Sn is equal to S. That equal to 1. Here you can also take that limit of for this, so limit of n by n square plus 1. That equal to here n square will goes outside, it will give the same value is here 1 by square root of 1 plus 1 by n square. If I take n square common out, 1 plus 1 by n square, n cancel out, we will get this value. That equal to here same value 1 by square root of 1 plus 0. That equal to what happen 1, right? This limit and this limit 0, the middle limit is 0, therefore sorry, this is limit 1, this limit 1, the middle one also same limit. That means so which implies limit of 1 by square root of n square plus 1 plus 1 by n square plus 2 plus dash 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 1 by n square plus n, that equal to also 1, right? So this is the way we have to show the problems, right? So this kind of problems very important for interest type as well as examination point. So you have to keep it in your mind and practice well, right? Here I am explaining this problem. Okay, limit of 1 by n square plus 1 plus 1 by n square plus 2, that as 1 by n square plus n, that equal to 1. Just now I explained. Okay, so just now already we shown this, no need to worry, apply here. So here same problem, by apply Sandwich theorem we will get this value. Okay, same again we have to take that limit of 1 by 1 n plus 1 over power lambda plus 1 by n plus 2 over power lambda plus that as 1 by n plus n whole power lambda equal to 0 for lambda greater than 0. So limit of this will you have to show that this is 0. Let I am taking that 1 less than or equal to m less than or equal to n. So 1 plus n whole power lambda less than or equal to m plus n whole power n lambda less than or equal to n plus n whole power of lambda. So this will what happen 1 by 1 plus n whole power lambda greater than 1 by m plus n whole power lambda less than 1 by n plus n whole power lambda, right? This is if I so I by the sign will changes, right? This inequality I am written as 1 by n plus n whole power lambda less than or equal to 1 by m plus n whole power lambda less than or equal to 1 by n plus whole power lambda. If m is equal to 1, we will get this inequality here m equal to 1. If m equal to here in place of m we will get 2 plus n whole power lambda. If m is equal to n we will get 1 by n plus n whole power lambda. By adding above inequalities and inequalities, see after adding this will be 1 by n plus n whole power lambda plus 1 by n plus n whole power lambda plus 1 by n plus 1 whole power lambda less than or equal to 1 by n plus 1 whole power lambda plus 1 by 2 plus that as 1 by n plus n whole power lambda is less than or equal to 1 by n plus n whole power lambda plus 1 by n plus n whole power lambda, that as 1 by 1 plus n whole power of lambda. Here how many lambdas are n plus n whole n plus n whole power lambdas are there? N by n plus n whole power lambda less than or equal to this. So here how many n's are there which is less than here less than or equal to less than or equal to n by 1 plus n whole power of lambda. So okay, what I'm doing here, I will take n common out, then this will what happen, n, if I take common out, n power lambda will comes, uh, n by n power lambda. So see what I'm doing here, if I take n by n plus n all power of lambda is there, and right hand side what we have here, n by 1 plus n all power lambda is there. Left hand side we have n by n plus n all power of lambda is there. So limit of I is for this. So if I n common out, then what happen here? 1 by 2 power of lambda and n power of lambda minus 1. Okay. If I apply limit for this, so 2 power of lambda, 2 power infinite, that equal to infinite, then infinite. Okay, so this lambda is positive here, so this will be 0. Okay, either this will be 0 or finite, maybe this also if I take, so this will be 0. Again n by n plus 1 lambda. So if I limit for same value, you can take n common out here, n power of lambda minus 1 whole power 0, that will be 0, that also 0, right? By apply Q theorem, this will be 0, this will be 0, the middle one also 0, this equal to also 0, right? Here bracket is here, lim of this equal to 0, right? Corollary of Q theorem, let Sn comma Tn are two sequences, and if mod of Sn less than equal to mod Tn, okay, and if lim Tn equal to 0, then lim Sn equal to 0. Mod Sn less than equal to Tn, for all n belongs to n, if lim Tn equal to 0, then lim Sn equal to also 0. For suppose problem I am taking Sn equal to minus 1 power of n. Sn equal to minus 1 power of n by n. Sn less than equal to what happen here? This is Tn. Mod Sn equal to minus 1 power of n, that equal to n. This is 0. This is also 0 by apply this. Mod Sn by less than equal to what we know, that 1 by root n. So this is 0. This is also 0. Right. So this way we have to take other problems also. Okay, some other problem. If Sn equal to 1 by 1.2 plus 2 by 2.3 plus 3 by 3 by 4 divided as 1 by n into n plus 1, then show that Sn is converges. We have to show by using problems. Limit theorem, directly show that. I am writing Sn is equal to 1 by 1.2, 1 into 2 here, 1 point nothing, plus 1 by 2 into 3 plus 1 by 3 into 4 plus divided as 1 by n into n plus 1. This can be written as 1 by 1 minus 2 plus this can be written as 1 by 2 minus 1 by 3. You can do here. So if I LCM do, then what happened? 2 minus 1 equal to 1, 1 into 2 plus, if you write this is 3 minus 2 is equal to 1, 2 into 3 plus 1 by 3 minus 1 by 4 plus as 1 by n into minus n by. Sn equal to 1 minus 1 by n plus 1. Lim Sn equal to lim of 1 minus 1 by n plus 1. Lim of 1 equal to Sn equal to 1. So therefore Sn is converges to 1. Find the limits of the following sequences. Right? n by 5. Okay, just to simply apply limit here. If n gets take common out, we will get this will be here numerator we have n times this will be infinite, that equal to compulsory 0 only. Okay, because the power is higher. Here the power is higher, then this is limit. If I apply limit here, this will be infinite. Because the power of n square is so greater than numerator, that will be 0. If power of n square, if numerator is greater than denominator is greater than numerator, it will be 0. If the power of numerator is greater than denominator, it will be infinite. It will be infinite, this will be, and that's why I am writing as n square plus q, and then it can come out. Lim m equal to infinity, this is equal to 1. This 1 plus 0, infinity minus infinity by 0, infinity by 1 equal to infinite. Prove the following. So lim of n cube plus 6n square plus 7 4n cube plus 2. So simply what you do here, this is interest per question. So this is where these are very easy. Here you can take and count out n cube. So I am taking count out n cube. So I will get here 1 by 6 plus 1 by 3 cube. Apply limit both side here. If I limit this equal to this, so n cube cancel out. Lemma of this equal to lemma of 1 plus lemma of 6 by n. This is equal to 1. This is 0. This is 0. 4. This is 0, 0. That means 1 plus 0 plus 4 equal to 0. 1 by 4 that equal to 4. Here also can take the n can cancel 1 by 1 plus n. Apply limit here 1. 1 plus 1 by that equal by here 1 n is missing. Okay. This is 1 plus so 0 by n and cancel is cancel 1 plus 1 by n. This is 0 1 plus 0 that equal to 1. So you can take n and cancel of 3 by 6. 3 by 6 nothing but 1 by 2. Simply you can take that. And then get cancel of 3 plus 7 by n. 6 minus 5 by n. This is also lemma of 3n plus 7. See n and cancel of 3 by 6 that equal to 1 by 2. Here lemma of 17 by here is n power 5 n power 5 can cancel out 7 by 23. It is easy. Otherwise we can take that n power 5 it cancel out, take 1 out. I simplify this, apply limit, we will get 17 by 23. Lemma of 17 n power 5 plus 73 n power 4 minus 18 n square plus 3 by 23 n power 5 that equal to 17 by 23. Lemma of this equal to 1. Okay. Here take that lemma of n cube, you can take an n cube, here 1 by 1, the other things are less than n cube. So that will be answer 1 inter type question. The power of, if I take that, the powers are, the quotient of powers will be the limit of the sequence, right? Simply here, if I do that, you can take the n cube common out. N cube common out, what we get here? 1 minus 2 by n square plus 1 by n cube. This 1 minus 0 plus 0, that is 1 minus plus 0, that equal to 0. 1 plus 0 plus 0, that equal to 1. Lemma of n cube equal to, this is 1. Okay. So this is very important. Discuss the nature of the sequence, right? Discuss the nature of the sequence. So r power n, let r is equal to 1. If r is greater than 1, lemma of r power n equal to 1, right? I am explaining this, right? So we would like to discuss the nature of the sequence. Right. So here I am taking this is okay. Here I am taking this is 0 minus 1. This will be plus 1. Okay. That means I would like to find the nature of sequence in 5 cases. If it is r lies between here, 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 okay, here. Okay, so these cases I would like to show that. So otherwise you can take that this case is here I am taking that I would like to take that r is lies between 0 less than 1, 0 less than or equal to 1. I am taking this. If r is greater than 1, if r equal to 0, if r is lies between minus 1 to 0, so if r is less than, yeah, if r is equal to less than greater than equal to minus 1, what happened? So these cases I would like to say. Case 1, right? Case 1. Okay. So case 1. Here if r is greater than 1, my case is from I am going to write here if r is greater than 1, which implies what happened, r power n is greater than 1. Here if I r greater than 1, r power n is greater than 1. In this case I am taking this is my r, like that r is greater than 1. Apply lemma r power n. Lemma r power n equal to what happened, lemma r power infinite that equal to infinite. Why? Because 1 is greater than infinite 1. r greater than r power n is also greater than 1, this is lemma of uniformity. Therefore Rn is not converges. If I take that r greater than 1, Rn is not converges. If r is equal to 1, if r is equal to 1, then what happen? R power n equal to 1, 1 power r equal to 1, lemma r power n equal to 1, r power n is converges if r equal to 1. If 0 less than or equal to r is less than or equal to 1. Okay, so if in this case, if 0 less than or equal to r less than 1, so what means here r, this is r. In this case, what happen? I am taking that the value is lies between 0 and 1. For this, I am writing here r is equal to 1 by 1 plus h for r h greater than 0. R equal to 1 by 1 plus h for h greater than 0. So if I h is any writing, the value must be lies between 0 and 1 only. The value must be lies between 0 and 1. So which r power n is equal to what happen? 1 by 1 plus h. Here r power of n is equal to 1 by h plus. By apply binomial theorem for this, so r power n is equal to what happen? 1 by 1 plus nh plus n into n minus 1 by whole square plus h over n. So apply binomial theorem, 1 plus x whole power n equal binomial theorem. This is why you know this is the theorem. By applying theorem, this we will get 0 less than or equal to r power n 1 by nh plus divided as. This term 1 by nh plus h plus n by n minus 1 that is called plus divided as. This term is less than by 1 by nh. 1 by 1 plus nh is less than 1 by nh. 0 less than equal to r power n less than 1 by nh. Apply limit 0 is equal to 0. Lemma of n by h is equal to 0. By Sandwich theorem, what happened? Lemma of r power n equal to 0. The middle one also 0. Which implies r power n is converges to 0. R power n is converges to 0. Case 4. Right. If minus 1 less than r is less than 0, if minus 1 less than r is less than 0, let r is equal to minus s, which implies minus 1 is less than minus s is less than 0, which implies 1 is s greater than 0. Right. Why I am taking the here minus 1 less than r? Already we know that one property. By using that property, I want to explain this. For that, I am writing here r is equal to minus s. If I substitute r equal to minus s, what happen here? Minus 1 is less than minus s is less than. That means here in place of r of x minus l. This can written as multiply this by minus what we get here 1 is greater than s is greater than 0, which implies 0 less than s less. Which implies limit n equal to 0. Already we know that if in this case lemma r power 0, that means limit n is equal to 0. S is nothing but minus 1 whole power of r equal to minus s, right? R power equal to minus 1 whole power n, equal to r power n equal to minus 1 whole power n. So Sn equal to 0. This is bounded. This is 0. This is also 0. By already know that minus 1 whole power is bounded. Limit n equal to 0. Therefore this value is 0. Therefore lemma of r power n equal to 0. R power n is converges to 0. If r is equal to minus 1, r power n equal to minus 1 whole power n. Already we know that this is not converges. Case 4. If r equal to minus 1, r equal to minus s, that means minus s, I am substituting here r equal to minus 1, then r equal to minus s, I am taking here s is greater than. Already we know that limit n equal to infinite. R power n equal to minus 1 power n, that equal to infinite. This is infinite, this is bounded, that also is not also converges, right? So that means we have discussed that r power n is converges if minus 1 less than r is less than or equal to 1, or mod r less than 1 and r is equal to 1. R power n is not converges. So r power n is not converges for mod r less than 1 r equal to minus 1. What? Lemma of r power n equal to 0 if mod r less than 1 and minus 1 are 0, right? If I take that lemma of 1 by 2 power n, lemma of 1 by 2 power n equal to what happen? R equal to 1 by 2, right? So which is less than 1, the limit 0. If r equal to minus 1 by r equal to minus 5, which is less than 1, mod r less than 1, right? This is less than 0, this also 0, right? So these end the applications of Q's theorem and Q's theorem problems. So this end lecture, right? Thank you for watching this.